let's talk about some partial derivatives. Let's say we had something like, but not exactly, f of xy equal to 2x to the 7th plus y to the 4th minus x cubed y squared. Okay. We would like to find all the first and second partial derivatives. Just a reminder, and we're taking a partial derivative with respect to a variable, we're treating the other variable as a constant. So if I want to find fx or del f del x, that's going to be 14x to the 6th. The derivative of this part is going to be 0. And the derivative of this part is going to be 3x squared times the constant y squared. No big deal. Fy, or del f del y, you don't need to write both. I'm just pointing out that either notation is valid, so you're going to see both probably, unless your professor specifically really likes one over the other, but I don't think that's the case. That's going to be, well, let's see, the derivative of this constant is 0. The derivative of y to the 4th is 4y cubed. The derivative of x cubed y squared is x cubed times 2y. Or I would probably write it as 2x cubed y. We did a lot of this today. Yeah. All right. Welcome. Let's see. What else did I want to say here? We should do the second partials as well. So there are how many second partials? I mean, really, there's only 3, but there's 4. Right? There is fxx, fyy, fxy, and fyx. Or del squared f del x squared, del squared f del y squared, del squared f del y del x, del squared f del x del y. Remember, for the mixed partial, the notations have different order. This means do x first, then y. This means do x first, then y. Because when I see a few confused faces about that last thing I said, right? This notation, I think, is maybe, I don't know if obvious is the right word, but it's straightforward. Just whatever letter you see first, that's what you refer to instruct to first. This notation really means take the derivative with respect to y of the derivative with respect to x. So you do x first, and then you take the derivative of that with respect to y. Let's actually find them. So del squared f del x squared is the derivative of the thing we already found. The derivative with respect to x of the derivative with respect to x. That's not too bad. And that's going to be, well, it's a little bad. 14 times 6, not my favorite. That's going to be 84. 84, yeah. 84x to the 5th minus the derivative of 3x squared is 6x times the constant y squared. Del squared f del y squared, or fyy, is going to be the derivative with respect to y of the derivative with respect to y. So we're going to differentiate that with respect to y again. We're going to get 12y squared minus that x cubed is a constant. The derivative of 2y is just 2. So we're going to get 2x cubed. Also, for those of you on Zoom, feel free to use the chat to ask questions. Yeah. All right, now what should happen, I'm going to say this again. This is not true for every function you'll ever see in the world, or for every function in 2 variables. But for any normal function, it is going to be true that these mixed partials are the same. You have to try, you have to work really hard to make up a function of x and y where those mixed partials are not equal to each other. We're not trying that hard. Okay. So I'm taking the derivative with respect to y of the partial with respect to x. Well, the derivative with respect to y of this is going to be 0, and the derivative with respect to y of this is going to be 3 times x squared times 2, or I should say negative 3 times x squared times 2y. And I would write that as negative 6x squared y. And the derivative of this is going to be the derivative with respect to x of the derivative with respect to y. That's going to be the derivative with respect to x of that. Derivative of 4y cubed is 0. Derivative of x negative x cubed is negative 3x squared times 2y. And oh yes, they are the same. Oh, sorry, I can't see it. I can zoom out just a tiny bit. Okay. So yeah, just want to really want to point out there, but my nose is really itchy. Yeah, that this and this are the same. And again, I just want to state it is generally not always true. There are weird freaking examples where fxy is not equal to fyx. But they're very complicated to contract. I think I have an example of one somewhere I can post on Canvas for you guys if you want. It's not really worth our time to look at in class, but I just want to point out there are examples of functions where it is true, it is not true that fxy equals fyx. Yeah.
Okay, first off, what's the little like d thing called?
Del.
Del. Okay. So for fxy, you know how you wrote del and then over del y?
So I wrote so for fxy,
yeah.
I wrote del squared f over del y del x.
But and then the equal sign, you wrote del y for that part and then also for the second one. But shouldn't it be del x?
Sorry, so where specifically?
Right there. Yeah.
So what I'm saying is del squared f del y del x means take the derivative with respect to y of the derivative with respect to x.
And then also for the next one?
I'm replacing del f del x with what del f del x is equal to. Right? That is the derivative with respect to x. That is the derivative with respect to x.
So when it's fxy, you do like del y, and then fyx, it's del x.
So, yeah. So I should be over here. Sorry, I always want to point that. So let's go through the whole list. Fx, this means I'm taking the derivative with respect to x. So I took this function, differentiated with respect to the variable x. Fy, same deal. I took the derivative of this with respect to y. We also write del f del x for fx, del f del y for fy. Fxx means I'm just taking the derivative with respect to x twice. So I did the derivative with, in fact, you can also write this in more colors. You could also write this as del x of del f del x. The derivative with respect to x of the derivative of f with respect to x. And this one here, fyy, is del y of del f del y. The derivative with respect to y of the derivative with respect to y. fxy, writing it this way means you differentiate with respect to x first, and then you differentiate that with respect to y second. So we do the derivative with respect to x first. We get 14x to the 6 minus 3x squared y squared. And then we take the derivative of that with respect to the variable y. So we're doing the derivative with respect to y of the derivative of f with respect to x, or x first, y second. This one's the opposite. This one's y first, x second. Del squared f del xy is the derivative with respect to x of the derivative of f with respect to y. Or as I would really read it, you take the derivative with respect to y first, and then you take the derivative of that with respect to x. So we did y first. The derivative of f with respect to y is 4y cubed minus x cubed times 2y. And then we did the derivative of that with respect to x. Now, the nice thing here is that almost all the time, it should be really 100% of the time in this class, these two should be the same. Now, I still would strongly recommend making sure you get the order correct, because someone's definitely going to be Maybe not definitely, but it's a good chance that someone will notice if you've done it in the wrong order and be like, that's not exactly right. So just do it in the right order. Other questions? Yeah. So one second, I want to be very clear about the language around these things because it is important. When you say f of x, if anyone, they think you mean the function. So specifically, when we read this, we really should say fx, nothing else. You could say f sub x if you wanted to, but f of x really does mean f parentheses x. So not to harp on that, just I want to make sure that everyone's saying and thinking of the right things.
Okay, so rephrase f sub, f subscript double x.
Sure, or fxx as I would
Yeah,
say.
or fx or fyy.
Mhm.
That's the second partial derivative, and then the x, xy are the mixed partial.
Yeah, we typically refer to these as just the mixed partials, although really they're the mixed second partials. Because you can have, there are lots of other mixed partials. Like you can do crazy things like fxxy or fxyx or fxxxy. Like you can do as many derivatives as you really wanted to. It would be kind of silly, but those are all mixed partials when you're using more than one variable in your numerous differentiations. Yeah, good question. Yeah. Other questions? Welcome. Thank you. So, how does fxy work? fxy is you take the derivative with respect to x first, y second. Let's do another example. Yeah. Okay. Oh, come on. Oh, crap, these are stapled together with a weird staple. Okay, so they're not really stapled, it's like a pretend staple that the copy machine does. And let's look at this function. F of xy equal to x divided by x plus y. Yeah, all right. So let's find some partials first of all. So we're just going to start off with the derivative with respect to x. And I'm going to use the quotient rule. I'm going to do the bottom times the derivative of the top minus the top times the derivative of the bottom, which is going to be, what is the derivative of the bottom going to be? Just 1, right? Because I'm differentiating with respect to x. So the derivative of the bottom is 1 plus 0 divided by the bottom square. And since we are planning on taking higher order derivatives, right? We're trying to take the second partials. We should simplify our first derivative. It's going to be in our best interest to do so if we're planning on taking more derivatives. So that's x plus y minus x over x plus y squared. And that simplifies as just y over x plus y squared. And I might actually write this as y times x plus y to the negative second for when I take the next derivative. It's going to be a little bit easier. How did you get that as the numerator? So you mean the x plus y minus x there? So I'll just reiterate, use the quotient rule. It's the bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is also 1. Let's look at the other one. Let's look at fy, the partial with respect to y. So you could use the quotient rule again, but let's do it a little bit differently. Let's instead think of our function as x times x plus y to the negative first. X is a constant. So I have a constant multiple of x plus y to the negative first. So my derivative is going to be x times the derivative of x plus y to the negative first. This is going to use the chain rule. It's going to be -1 times my stuff to the negative second times, what's the derivative of that stuff inside there? Good old 1, once again. Or you could say 0 plus 1, right? Because the derivative of x is 0, 0 plus 1. And simplifying this just a tiny bit, I'm going to write it as negative x times x plus y to the negative second. It also would have been perfectly fine to use the quotient rule here. I'll just point out that if you use the quotient rule, it can be a little bit dicey. Bottom times the derivative of the top is 0 minus the top times the derivative of the bottom is 1 all over the bottom squared. Oh yeah, look, we're getting the same thing. We're getting a negative x divided by x plus y squared, or a negative x times x plus y to the negative second. It's really the same. Don't hesitate to ask questions if you got them. People on the chat, sorry if I'm missing your questions. I've tried to get to them, but like definitely if you see me not addressing your question, feel free to unmute yourself. It's totally fine. You might scare the crap out of me, but that's all right.
Is that x plus y times 0?
It is. So this whole part just becomes 0. This is equal to negative x over x plus y squared, which is the same as negative x times x plus y to the negative second. Yeah.
Can you explain the chain rule like one more time?
Yes, the chain rule. So in fact, we're going to talk more about that hopefully today. Very, very generally, the chain rule says when you take, so when I think about it is if you have a function of some stuff. So for example, I'm going to come back to this in a second. So chain rule example. If I was taking, I'm going to do a function of one variable. If I said like the derivative with respect to x of, I don't know, sine of x plus e to the 2x all to the 5th power. When I think of taking the chain rule derivative, I think of I've got some stuff to the 5th power. What's the derivative of x to the 5th? Thank you. The derivative of some stuff to the 5th instead of x to the 5th is 5 times your stuff to the 4th power. But then we have to multiply by what? The derivative of the stuff. So that's always what I'm thinking of when I change it. I've got a function of some stuff, and the derivative is the derivative of the outer function, 5 times whatever to the 4th. Leave the inside stuff alone, and then you have to multiply by the derivative of that stuff. The derivative of sine of x is cosine of x. The derivative of e to the 2x requires the chain rule again. What's the derivative of e to the x? E to the x. What's the derivative of e to the stuff? E to the stuff times the derivative of the stuff. Right? It's always the thing that we're looking for. So the derivative of e to the 2x is going to be e to the 2x times 2. Or e to the stuff times the derivative of the stuff. Why was I able to use the same equation from fx and fy? Well, so when I'm taking the partial derivatives, I'm still taking the partial derivative of the same original function. So I'm differentiating this original function. And it's just that a lot of the pieces end up being the same when we differentiate with respect to x or with respect to y, especially when we're using the quotient rule. Sorry if I covered that up too quickly. I can't see all the things. Need more eyes. But yeah, so that's kind of the chain rule in a very quick nutshell there. If you've got a more complicated function than just like a function of x, you think of the inner part as stuff. And you do the outer derivative, and then you always multiply by the stuff every single time. All right, let's find. Oh yeah.
For derivatives, is there a difference between using like just a d over dx or the del?
Yes, there is a big difference. The difference here is that when you write d dx, you mean that your function is a function of just x and no other variables. But when you write the del, you're implying that it's a partial derivative, meaning the function is a function of more than just the variable you're differentiating with respect to. Yeah, that's the difference. If you see d, it means function of one variable. If you see del, it means function of multiple variables. I mean, really, it means partial derivative and using partial derivative because All right, let's find the second partials. Let's find fxx, fyy, and both of the mixed partials, fxy and fyx. So fxx. All right, so I'm taking the derivative with respect to x of the derivative with respect to x. And luckily, y is just pretending to be a constant here. So the derivative of a constant times some function is the constant times the derivative of that function. And the derivative of some stuff to the negative second power is -2 times that stuff to the negative third times the derivative of the stuff. If you wanted to simplify this, you could simplify it as -2y times x plus y to the negative third. Or you might write it as -2y over x plus y. Question? Sometimes I wish I had less facial hair, because the facial hair is really like just pulling this thing. Like I don't have like, I mean, you guys can see like, it's not like I have like, I shaved yesterday, but you know, there's a lot of hair over here and it's really kind of pulling. All right. I mean, it doesn't hurt. It just is pulling the mask off my face, which is terrible. Not the best fabric. Okay, so fyy. We're going to take the derivative of y, or sorry, derivative with respect to y of the derivative with respect to y. All right, let's see what happens here. So again, this negative x gets to pretend to be a constant and it just hangs out. Constant multiples hang out. Derivative of some stuff to the negative second, once again, is -2 times our stuff to the negative third. And the derivative of our stuff is 1. Now, I will point out, just for clarity, here, this 1 is really 1 plus 0, right? The derivative of x is 1, the derivative of y is 0. Here, this 1 is really 0 plus 1. The derivative of x is 0, the derivative of y is 1. Because we differentiate with respect to a different variable. All right, and then we could simplify that as positive 2x over x plus y cubed. Let's find the mixed partial. Let's do fx first, fxy first. When I talk about mixed partial derivatives, I feel like I'm talking about mixed martial arts. Mixed partial, no, okay, yeah, mixed partial derivatives. So we're doing del x, and we're doing, oh, no, see, no, I'm right, no, I'm wrong. I want to do x first, then y. I don't want x on the outside. I want y on the outside. So I want to do y second, and I want to have done fx first. Right, we're taking the derivative with respect to y of the derivative with respect to x. We did x first, we're doing y second. This one's actually going to be more work than the other ones, right? Because now we have to use the product rule. If I'm differentiating with respect to y, I have the function y times the function x plus y to the negative second. So this is my first piece, and all of this is my second piece. What's the derivative of the first piece? Good old 1. We leave the second piece alone. Plus, then we flip it, or we switch it, or vice versa, however you want to say it. We leave the first piece alone, and we multiply by the derivative of the second piece, which is going to be -2 times x plus y to the negative third times 0 plus 1. That's not very nice looking. It's okay, it happens. Yeah, this one might have been better to do it. So it really is interesting that sometimes it's really better to do it as a chain rule, or sorry, as a product and chain rule. Sometimes it's really better to use a quotient rule. So can I fit this in here? I kind of jam myself up on how much room I have left here. We can probably fit it in right here. So fyx is going to be the derivative with respect to x of the derivative with respect to y, which was this thing here. Negative x over x plus y squared. Using the quotient rule, it's the bottom times the derivative of the top, which is -1, minus the top, which is, top times the derivative of the bottom, which we need the chain rule for, 2 times our stuff to the first power times the derivative of our stuff, which is 1 plus 0, all divided by the denominator squared. I don't know, it kind of feels like both of those are terrible. Are they the same? Well, I mean, they should be. That's what I said. It's kind of what I promised you all. I try not to make promises that aren't true. They are the same, but we should probably explore that just a tiny bit more. Let's double check. Do a little simplifying here. So let's look at fxy first. That looks gnarly. I'm going to do something. I'm going to rewrite fxy. Now, here's what I would say. You probably don't need to write this part down. You certainly can. I mean, you're always welcome to write whatever down you want. I'm not doing anything here that's really super useful other than just verifying that these really are the same. So if you don't want to write all this garbage down, you really don't need to. But let's check. fxy is, I'm going to write it as 1 over x plus y squared. And then that's going to be a minus 2y over x plus y cubed. And I'm going to get a common denominator. Which isn't too bad, actually. So this ends up being x plus y minus 2y all over x plus y cubed, which is x minus y over x plus y. Let's look at the other one, which looks a bit gnarlier. I'm going to do a, let's see, like, can I really do a lot of simplifying here? Let's just write it out again. I've got -1 times x plus y squared. Minus a minus is plus 2x times x plus y. And I'm worried. I'm not that worried. What can I factor out from the top? Yeah. I factor out an x plus y. I'm left with a -1 times an x plus y plus a 2x divided by x plus y to the fourth. Cancel one of those and one of those. I'm left with a -x plus y plus a 2x, sorry, -x minus y. I got to distribute that. Plus 2x all over x plus y cubed. And we got the same thing. That is definitely equal to x minus y over x plus y cubed. So yes, it is true that for this function and for most functions, we will see it's going to be the case that the mixed partials in either or are the same, which is good because it's a pain in the butt to have to find them. All right, let's see what time is it. Okay. Yeah, okay, one more example. Keep things in order here. Sorry, I want to more later when I post the notes. We can also take partial derivatives of functions of more than 2 variables. Oops, that's not that. For example, if we had to say f of a function of x, y, and z equal to say x squared times sine of 2y plus 6z. We can totally take all the mixed partials you want. Fx is going to be 2x times sine of 2y plus 6z. That's it, right? As far as x is concerned, sine of some stuff without x's in it is a constant. Fy would be x squared times cosine of 2y plus 6z times what? Times what? What did I do? What rule did I use? Start with the ch. I use the chain rule, right? I'm taking the derivative sine of some stuff. Derivative sine is cosine. The derivative sine of some stuff is cosine of the stuff times the. Right. I said stuff. You all said, oh, the derivative of the stuff is what we need. But the stuff is 2y plus 6z, and we're differentiating with respect to y. Why don't you all find fz? Moving things around. Too many things here. Cool. There we go. Okay. All right. So for fz, it's almost the same as fy. It's x squared times cosine of 2y plus 6z times. Exactly. There's your fz. Not too terrible. All right. I don't want to exactly show you guys your homework problem because I feel like there's only so many homework problems to do. But I do feel like that first homework problem he's asked you guys is a little bit, I think it's a little bit confusing. So I just want to address it briefly here. And then we'll move on to talking about some tangent planes, some linear approximations, linearizations, tangent planes, same deal. So I'm going to make up something a little bit different. Let's consider this function. What kind of gnarly thing do I want to make up here? It's going to be similar. Sure. Let's say it's 9y squared minus x squared over. Sure. Let's make it 2x squared plus y squared. And we're going to do two things. Thing one, we're going to find what the level curve of 0. So which is super funky. So did I make it? Let's see if I made a dumb mistake before I really do this. No, I should be fine. I should be good. Yeah. All right. Let's actually do that part second though. Let's prove that the limit's not 0. Or sorry, the limit does not exist. I mean, it also is not 0, but it definitely is a little bit more than that. It doesn't exist. So let's take a couple different paths. Let's take the path. So here it's actually really easy to just use the paths x equals 0 and y equals 0. Take the path x equals 0. Then you're left with the function f of 0y is, let's see, it's 9y squared minus 0 over y squared, which is just 9. So when x is 0, it's 9. So I should really say on this path, the limit as y approaches 0 on the path x equal to 0 of 9y squared over y squared is the limit as y approaches 0 of 9, which is 9. But really what you should be thinking of is like in 3 dimensions, if you were specifically on the x equal, I should point at you on the x equals 0 axis. Sorry, x equals 0 is not an axis, it's a plane. The x equals 0 plane is the yz plane. Sorry, I got that totally backwards. On the yz plane where x equals 0, the function is equal to 9 the whole time. So on the plane that is the wall, the function, maybe it's some curve, it's doing this kind of thing, but specifically on that plane, you got y equals 9. Sorry, you get z equals 9. Sorry, right? That's fine. And then on the y equals 0 plane, which is the xz plane, which is the plane that kind of tries to slice you, right? It's the one I'd be cutting you with like this, not like this, not like this, like this. Well, then we're going to get f of x0 equal to negative x squared over 2x squared, which equals negative 1/2. So the limit as x approaches 0 of this function on the path y equal to 0 is going to be the limit as x approaches 0. I'm just going to write it as negative 1/2. You get negative 1/2. And that is enough to say that the overall limit doesn't exist because you got two different values. So the limit as x, y approaches 0, 0, definitely non-existent. But now here's a more interesting question. What is the level curve when c equals 0? So the question really is, and I felt like, at least at first, I thought it was really kind of hard to answer. When does 9y squared minus x squared over 2x squared plus y squared, when does that equal 0? Well, it turns out a lot of places. Here's what I would do. So specifically, there's one place we know it's not equal to 0, or really anything, at the origin. At the origin, this thing is totally undefined. Right? What happens when you plug in 0, 0? You get 0 over 0, which is. But if we want to see where this is equal to 0, where if you want to see where a fraction is equal to 0, you really want to see where the top or the bottom? Actually, the top. Right, so if the bottom is 0, we got problems. What's 5 divided by 0? A lot. Let's see, how many times does 0 go into 5? Too many. Right? Like as many times as you want. 0 can keep going into 5 and you're never done. It's kind of like infinite. How many times does 5 go into 0? None. Right? 0 divided by 5 is 0. 5 goes into 0, 0 times. 0 times 5 is 0. Do the subtraction. Oh, yeah, you're good. So 0 divided by anything is totally fine. What should I try to back that up just 1 second? 0 divided by anything that's not 0 is totally fine. 0 divided by 0, as we've seen, is a problem, like in this example. So this equals 0 when the numerator equals 0. And we could be a little bit more specific, and the denominator doesn't. But we're not going to worry too much about that. Well, that's not too terrible. We can solve that. I'm going to isolate y. So 9y squared equals x squared. Y squared equals x squared over 9. And now what? It's what you want to do. Oh, of course, always, yeah. Never feel like you need to hesitate to ask that. I'm always trying to put the paper in the screen. So if it's not, just let me know. So what am I going to get here? Y equals x over 3 is one of the parts of the level curve, but that's actually not the whole level curve story. Because y could be positive x over 3, but y could also be negative x over 3. Think about it. If y was negative x over 3, would y squared equal x squared over 9? Yeah, right. Let's see. Y squared would be negative x over 3 squared, which is negative x over 3 times negative x over 3. Oh, yeah. So here are our interesting level curves, or I should say, our level curve, period, 1. This is one level curve when c equals 0. And it looks like this. Now, I still don't think that's particularly informative. I really wanted to do is show you guys something, which I think is kind of neat. You know me, I'm a big fan of using the Desmos, or not the Desmos, sorry, where'd you go? The other graphing thing, Geogebra. I know I'm not sharing it with you yet. I'm working on it. I have to find the thing first, graphing, Geogebra. And let me write the functions here so I don't jack it up while I'm trying to do it over there. So let's see. So we've got our function, which is z equal to 9y squared minus x squared divided by 2x squared plus y squared. Okay. Oh yeah, that's a real beauty. So let me throw this your way. Check that out. Let's look. Oh, see, now it's hard for me to do any kind of real meaningful zooming here. I'll close this. Yeah. So there's the curve. I really wish I could see a bit better. All right, one sec. I'm getting there. It's challenging to do this like this. Get back everywhere. I've clearly broken it. Oh, there we go. Okay. Cool. Finally, there's the curve I was actually trying to get to, or the surface. So take a look. Take a look at that little shadow right there. Those are totally the lines y equals 1/3 x and y equals negative 1/3 x. You kind of seem a little bit better like this. And if you really want to see them, check that out. That's totally the plane y equals x over 3. And it exactly is intersecting that surface in the plane z equals 0, or the level curve z equals 0. So hopefully this is at least a little bit illustrative as to what's actually going on here. Right? When you're finding the level curve of a surface like this, I should say, when you're finding the level curve z equals 0 or c equals 0 for a surface like this, you're really seeing where that flat plane cuts through the surface. And what's left is this little line, y equals x over 3, or this line over here, y equals negative x over 3. I'm sorry, for those of you on Zoom, you're left with, right, the line there, y equals x over 3, the line there. And in fact, if you tilt it this way, you can totally see the lines. There's y equals x over 3, there's y equals negative x over 3. Right, this is the top-down view. And I think, yeah, right there. Oh, except I've got it rotated slightly off. Right. Oh no. I can't do it, sorry. Maybe. There's the actual view, because right, there's the positive x-axis, there's the positive y-axis. Neat. All right, enough of that. So hopefully that will help you do the first problem on your homework, because it's very similar, but not exactly the same. Well, let's go ahead and talk about tangent planes. Linearizations. There's lots of ways of saying the same thing. I need a sip of water. And notes, yeah. So what I want to stress, first of all, about tangent planes linearizations is it's really, really, really kind of, as is true with a lot of multivariable calculus, it's very much the same as what you did with single variables. It's just kind of adding literally an extra dimension. But it's really not that different of a process. Also teach me to never, ever forget to put on my different mask. So recall, if you will, from 17a, the equation of a tangent line, tangent to y equal to f of x at the point x naught, y naught, is given by the following formula. Y minus y naught equals f prime of x naught times x minus x naught. And really, this is kind of, I mean, I don't want to say, this is how we find the equation of a tangent line, right? You find the slope of the tangent line. At the point, and then you use that slope to find the equation of your line that goes to the point x naught y naught. And then people often kind of rewrite this, the linearization. So when you do a linearization, you kind of have to isolate the variable you are linearizing. So we wouldn't write the linearization like this. We write the linearization as, and for some reason, when we do linearization, we like to pick x equal to a instead of x equal to x naught. I couldn't tell you why. I'm going to write it both ways. The linearization at x equals x naught would be, I'm just going to solve for y, but I'm going to call it L of x because it's a linearization. L of x equals y naught. Why not? Like, that's not clever. Plus f prime of x naught times x minus x naught. Or if we're linearizing at the point x equals a, y equals f of a, then we're going to get L of x equal to f of a plus f prime of a times x minus a. And for whatever reason, this is kind of the standard way of writing it. Although this is also perfectly fine. If you want to, you'd be like, hey, James, isn't that just f of x naught? And be like, it totally is. So that's how you do the linearization of a function at a particular point. And again, linearization, just fancy words for tangent line, right? When you're linearizing a function, you're saying, I want to make this small piece of a function look like a line. So I'm going to take the tangent line. Oh, it's the tangent line. That's it. All we're doing with multiple variables is we're going to be finding the tangent plane. This is like, oh God. Oh. Okay, so we could do that. Sure, let's do that. So what we used to use linearization for, well, I mean, there's a lot of things you can use linearization for. One of the things we would use linearization for is to something like this. Let's linearize the function f of x equal to the square root of x at a equal to 9, and then use it to approximate the square root of 8. And graphically, here's what's going on. Here's our square root function. And here is, say, the place where we are linearizing things at. The point 9, 3. Oh, yes, of course. So I'm going to draw my linearization. And pray that it comes out good. Yeah, it came out pretty good. Not sad about that. So there's my linearization. I suppose I should actually find the equation of this tangent line. But that's the idea. So my function is the square root of x, or x to the 1/2. My derivative is 1/2 x to the negative 1/2. And importantly, the place you are linearizing things at should always be a value that's easy to plug in. Right? It's easy to take the square root of 9. It's not easy to take the square root of 8. I don't know what that is. So that's the idea. And then we're really just going to use that formula. We're going to say, oh, yeah. And I suppose I could write a few things down. F of a is 9 to the 1/2, which is 3. And f prime of a is 1/2 times 9 to the negative 1/2. 9 to the negative 1/2 is 1 over the square root of 9, which is 1/3. And 1/2 times 1/3 is 1/6. So our linearization is f of a plus f prime of a times x minus a. That's going to be f of a, which is, where'd you go? 3 plus 1/6 times x minus 9. And that's telling us that the equation of this line. And now the idea is we want to use this linearization to approximate the square root of 8. Well, let's see. I'm going to try and draw a good picture here. Let's say that's 9. I'm going to make it a little bit exaggerated. I know 8's not like really that far over, but just bear with me. So if 8 were right here, there's the square root of 8. And if you go up just a tiny bit higher, there's the linearization evaluated at 8. See how close those are? Pretty close. You see what a good approximation the linearization is for the square root of 8? Question there, or just you look like you're kind of about to. Okay, cool. So I'll make sure I don't leave any questions on the table. So it's a good approximation. Now I will point out, if you were trying to use this to approximate like the square root of 17, that'd be a bad idea because 17 is kind of far away. They're going to move further and further apart from each other as you move away from the point where you're linearizing it.
For f prime of x, is that negative 1/2?
No, it's positive 1/2. It's a positive 1/2 times x to the negative 1/2.
And then also for f prime of a, it's the power of negative 1/2, right?
Correct. So what I'm getting there is a 1/2 times 9 to the negative 1/2 is 1 over the square root of 9, which is 1/3, or 1 over 9 to the 1/2.
Thank you.
You're welcome. So plugging in 8 here, I can say that the square root of 8 is approximately the linearization evaluated at 8, which is going to be 3 plus 1/6 times 8 minus 9. And simplifying that, we get 3 minus 1/6, which you could either write as a fraction. That'd be 18/6 minus 1/6, which is 17/6. Although I feel like that's not particularly, it doesn't really show us everything. If I actually write it as a decimal, 1/6 is 0.166666 forever. As evidenced recently on the, you guys watching Survivor? Anyone? No one watches Survivor? Okay. The guy like on Survivor said what 1/6 was as a decimal, like, and everyone was super impressed. I was like, really? That's impressive? Okay, fine. It's not impressive. But 1/6 is 0.166666 forever. Don't be impressed. And then 3 minus that is 2.833 forever. On the other hand, the square root of 8 is actually, calculator, come on. Square root of 8 is, I really don't love this calculator, but it's fine. It's 2.828 approximately. So the linearization does a good job for values of x close to 9 of approximating the square root of them, right? It's not bad at all. So that's what we're going to be doing in now multiple dimensions. We're going to be linearizing things, functions of 2 variables instead of 1. Instead of a tangent line approximating a curve, we're going to have a tangent plane approximating the surface. And since I'm a crap drawer, I mean, this is fine, but let me just show you this other lovely picture that my colleague Grant has drawn, which I think is very nice. So I'm going to say some words. I might as well, and we've got some things written down here. Here's the idea. In fact, let's kind of make the connections here. Go back. So we got room. Maybe we can make it. So tangent plane, y minus y naught, sorry, tangent line. Y minus y naught is f prime of x naught times x minus x naught. Tangent plane, very much the same idea. You're just adding in another variable. So instead of y minus y naught equal to the derivative times x minus x naught, it's now your output variable z minus z naught equal to the derivative with respect to x at the point times x minus x naught plus the derivative with respect to y at the point times y minus y naught. It's very, very much the same idea. You're just kind of extending it a little bit. And the idea is that this tangent plane at this point is a good approximation of the surface near that point. I kind of like, yeah. How much time have I got? Oh, I got 20 minutes. Cool. So, yeah, okay. So let's write some things down. Oh, someone came in. Oh, come on, mask. Don't be so unkind. Tangent plane to the surface z equal to f of x, y. Wow, my nose really itches. At the point x naught, y naught, z naught is the following. Z minus z naught equals the partial with respect to x evaluated at the point times x minus x naught plus the partial with respect to y at the point times y minus y naught. And then we do the same sort of thing, right? We solve for z as a function of everything else, and we write it as a linearization. So we're going to isolate z. We're going to get, I'm going to write it this way, z equals z naught plus the whole garbage again. It's a lot of writing, kind of. Notably, I should actually look at what he's got here. It didn't say, okay. Some people, instead of writing parentheses x naught, y naught, they use this vertical line with an x naught, y naught kind of in the subscript. That means the same thing. It just means the partial derivative evaluated at x naught, y naught. This means the partial derivative evaluated at x naught, y naught. You might see either notation. And then we're going to rewrite it as z is the linearization of the function of x and y. And it's equal to z naught, which is f evaluated at x naught, comma y naught, plus the rest of this stuff. Why would you write this in 3 different ways? Good question. No good reason other than this is kind of the standard way of writing it. But it's kind of a giant mess. I mean, it's not really that messy, but it's not pretty. And we don't get into it so much in this class, but there are ways of actually deriving this tangent plane equation. It's really kind of the same as a tangent line equation, and you could but you have to kind of get more into the 3 aspects of calculus, which is not what we're here for. Like, if you took the 21 series, you would totally be here for that, and we would talk a lot more about it. But we are really trying to get to the place where we talk about systems of linear differential equations. And this is just kind of a stepping stone along the path to get there. So let's do an example. And then let's talk about why we care about this at all. Find the linearization of the function f of xy equal to x cubed times y to the 4th at the point 2, 1, and then use it to approximate f of 2.2, 0.9. And not that you couldn't use a calculator to do this relatively easily, but calculating that by hand would be, I mean, again, not impossible, but a bit of a challenge, right? 2.2 cubed, not particularly nice. 0.9 to the 4th, not particularly nice. Manageable, sure, but that's not the point. So we're really just going to throw this formula at it. So I'm going to find all these things. So my x naught, y naught is the nice point where we are linearizing it. And let's find our partials. Actually, I guess, okay, fine. I suppose I could find f of 2, 1 first. So f of 2, 1 is going to be 2 cubed times 1 to the 4th, which is 8. My partial with respect to x is going to be, let's see, here's my function. Let me just write the function here. fx. So this is one of the reasons we've been talking about finding partial derivatives, because we use the partial derivatives to find the linearization of the surface. That's not the only reason, but that's one of the reasons. So that's going to be 3x squared times y to the 4th. And then evaluating it at the point 2, 1 is going to be 3 times 2 squared times 1 to the 4th. Sorry, 3 times 2 squared times 1 to the 4th is going to be 3 times 4 times 1. And fy is going to be the partial with respect to y, x cubed times 4y cubed. Oh, yep, of course. And then evaluating that partial at 2, 1 is going to be 4 times 2 cubed times 1 cubed, which is 32. So then we have all the pieces we need to make the linearization happen. So our linearization is going to be, I really don't want to write this out again. Let's just fill in the dots or the pieces. F of x naught y naught is going to be 8. Fx at x naught y naught is going to be 12 times x minus the x coordinate plus fy, which is going to be 32 times y minus the y coordinate. Now, here's what I'll say about this. People have a tendency to want to simplify this. Right? We could totally simplify this, but what I'll point out is you're not actually simplifying it. So if you take the time to do this and say, okay, I got 8 plus 12x minus 24 plus 32y minus 32. And then 8 minus 24 is negative 16 minus 32 is negative 48. You're wasting your time. Maybe not entirely. Maybe someone is asking you to do this. But you're wasting your time in the context of what we're being asked. Because when we get asked to do, we get asked to approximate f of 2.2, 0.9. So f of 2.2, 0.9, we're going to approximate that with the linearization. And now, in my opinion, and I kind of hope your opinion too, it's much easier to plug those values into this equation where things kind of simplify down pretty nicely versus plugging in there. I'd rather not figure out what 12 times 2.2 is or 32 times 0.9 is. It's much easier to be like, oh yeah, I'm going to have 8 plus 12 times 2.2 minus 2. Oh yeah, that's going to be nice. It's going to be easy. And 32 times 0.9 minus 1. And that's going to be a relatively straightforward calculation. 2.2 minus 2 is 0.2. And 0.9 minus 1 is negative 0.1. So I end up with 8 plus 12 times 2 is 24. So 12 times 0.2 is 2.4. And 32 times negative 0.1 is minus 3.2. In my mind, that is way better than plugging those values into this red equation here. So I would encourage you all, if you're finding a linearization of a function of two variables, stop here. Don't multiply these out and simplify it. Leave it like that, because usually you're going to be plugging in numbers that are close to that number and that number, meaning these pieces will be small and easy to multiply by their coefficients. In any event, we get 2.4 minus 3.2 is negative 0.8, and 8 plus negative 0.8 is positive 7.2. So f of 2.2, 0.9, which would actually be 2.2 quantity cubed times 0.9 to the fourth, is approximately 7.2. What is it actually? I don't know. You could use a calculator. This is though. I know it's poetry. Questions about that? Okay. So let's look at another example. An example with some biology implications. So here's a question from section 9.0. This is cool. Not one of your homework problems. Great. Not that I would really care if it was, since they're not really due anyway. But this is from section 9.3, number 22, in case you're curious. Here's what we've got. A model for the surface area of the human body. Interesting. Is given by the following. Surface area is equal to a function of W and H, which I'm assuming are weight and height, which is 0.1091 times weight to the 0.425 power times height to the 0.725 power, where weight, or W, is weight measured in pounds, and height is, or H is height, I would assume measured in feet. Oh no, inches, sorry. I would assume measured in the US system, right? If you're in pounds, you're definitely probably not also in meters. And S is square feet. So let's find the linearization of S when the weight is 160 pounds and the height is 70 inches. Okay, well, we know how to do this. We've got the whole kind of picture. I might start by writing it out just very generally. I might not. I might totally skip that. But you can start by saying, okay, I'm going to write that the linearization. So I should really say S. Come on. My function of W, comma H is going to approximately be the linearization, which we know is the function evaluated at W naught H naught plus the partial with respect to W at W naught H naught times W minus W naught plus the same exact thing except for the other variable. The partial with respect to H at W naught H naught and H minus H naught. I don't know if I find this actually helpful or not, but it's just something I've gotten in the practice of doing. I'm just saying, okay, I know what the formula should look like. Let me just write it out. And then we're just going to fill in all the pieces. Now, the pieces are going to be a little less nice here because our powers are kind of strange. That's okay. All right, so I'm going to find the mixed partials. FW, sorry, not the mixed partials, pardon me. Sorry, just the partial derivatives. No mixed partials here at all. Excuse my misspeaking there. I'm going to find the first partials. FW, so I'm going to take the derivative of this with respect to W. So I'm going to get 0.1091. The derivative of something to a power is just that power times the something to the one less power. Then 0.425 minus 1 is negative 0.575 times H to the 0.725. And when I plug in the point, 160 comma 70, I get approximately 0.0546. Now, I will definitely mention here, this is kind of an, I wouldn't say it's an atypical example, but it's a less typical example because most of the time when we're doing these linearizations, the values you're plugging in are kind of nice, right? Like the previous example, the 2 and the 1 were nice to plug in, the 2.2 and the 0.9 were not. Here, that's not what we have, right? Plugging anything into this function is terrible regardless of what you're doing. It's okay, sometimes things are terrible. In a similar way, the partial with respect to H is going to be the derivative of this with respect to H. So we're going to get, again, 0.1091. This is going to stick around, not changing, W to the 0.425. And then we're going to get times 0.725 times h to the negative 0.275. And if we plug in the same value, 160, 70, we're going to get approximately 0.213. And then if we actually plug, we also need to find this here. So f of 160, 70, plugging that into this equation is going to give us approximately 20.524. So let's write down what our linearization is. It's 20.524 plus 0.0546 times W minus 160 plus 0.213 times H minus 70. But let's write it actually down on a new page. What time is it? Okay, we got 5 minutes. Definitely enough time to finish this, I think. Yeah. So here's our linearization. It's that plus that times W minus the W value, which is 160 pounds, plus the partial with respect to H times H minus the H value, which was 70 inches. Okay, so now we're going to use this linearization. And here's kind of the idea. We've got some plane, and there's some, my plane is not the best looking, sorry, some surface, I should say. And there's a point on the surface, in this case, 160, 70, where we are taking the tangent to the surface. And it's touching right there, but it's kind of removed from it, right? And maybe we're going to use this plane to say, well, if we just change our x and y values a little bit, we would still be on, we'd be on the surface, the black surface, but it would be still pretty close to the plane values, just like on our curve, right? When we were on this curve here and we moved a little bit away from the point of tangency, the output values were still pretty similar to each other. The same idea is true here. When we move away from this point of tangency, as long as we don't move too far away, the values are a pretty good approximation of what's actually happening. So we want to approximate the surface area of a person weighing 162 pounds, who is 73 inches tall. Now, I will fully admit it's just as hard to do the linear approximation here as it is to actually plug these into the original function. In fact, it's probably even harder. And plugging into the original function is pretty easy. The original function, f of 162 times 73, is just our coefficient 0.1091 times 162 to the 0.425 times 73 to the 0.725. And that's approximately 21.271 square feet. This is the actual value. This is not the approximation. But what I want to say, right, is either way, you'd have to use a calculator to do this, right? There's no way you're calculating this without a calculator, unless you've got the most amazing brain I've ever seen. So I suppose there are people that can actually do this. I don't like this many people will probably do this in their head. But what we're doing is we're doing the linearization. And so we're throwing these numbers into this equation, which I guess isn't, I suppose you could do this without a calculator. No, I couldn't. You could, maybe. I can't. But I'm just saying, okay, my W value is 162 minus 160. My H value 73 minus 70. Then maybe I could pretend like this is moderately doable, I suppose. You get 20.524 plus 2 times that is 0.1 something. Ah, see, my brain's like not even there. Maybe no. That's not the point. But now I'm like, can I do it? Sorry. And then this is going to be 0.213 times 3, which is going to be 0.639. So you could actually do this without a calculator. I don't think you need to do that. This ends up being about 22.25. So pretty good approximation, right? Our approximation of 22, a little more than 22 square feet is not that far out from the actual value of a little more than 21 square feet. Big picture, we use these linearizations to approximate, right? That's the specific value, not generally. Because again, as you move further and further away from the point of tangency, you move further and further away from the function value and you get less good approximation.